A little bit of background. As Oliver was suggesting, I have a mixed background. I'm somewhere between a researcher gone horribly astray and more of a Silicon Valley software engineer who kind of dabbles in research. He had asked that I make some remarks about that duality. So I'll put those at the end if I don't run out of time. Sorry, unaccustomed as I am to public speaking. All right, so speaking of Silicon Valley, this is where I'm from. This is California, San Francisco. We're out here on the left coast of the United States. I pointed out some of our outstanding educational institutions, UC Berkeley up here. I worked for a while at UC Santa Cruz, which is actually down off the bottom of the map, a lovely coastal city nestled among the redwoods. And of course, Stanford University is here. And in this general peninsula, South Bay area are a pretty amazing concentration of high-tech companies. Google, Facebook, LinkedIn, Adobe, it's a very long list. And I work for one of those ubiquitous startups. It's called Matterport, and we're within a stone's throw of Google's campus. I was making this slide thinking about how to talk about the Bay Area, and I glanced out the window and said, well, that's kind of the thing. So this is literally the view from where I was typing my slides. This is San Francisco out here. These are the San Bruno Mountains, and this is the San Mateo here in the foreground. Anyway, it's a lovely area. And since my employer has kindly given me the week to come make this trip, I thought I would mention them briefly. So this is a rather unusual house not far from where I live, known as the Flintstone House. It was made in the late 70s based on the idea of organic architecture. So this is actually sprayed concrete construction that was formed over inflated weather balloons at some kind of steel cage. So this virtual tour is one of the things that my company does, our commercial applications in real estate sales. So these are basically spherical panorama images, but they are embedded in a 3D space. There's a mesh model that's captured. And so in this application allows you to walk around a house and get a sense for the spatial arrangement of the pieces of the house. Anyway, I don't want to take too much time with this. Oof. There we go. Anyway, that's Matterport. So a couple of words about some of the interests that have driven the work that I've done. I started as a child, as Steve Martin said, and I've always been fascinated with sort of complex motions, things like turbulent fluid flow and the collective motion of birds and fish. In fact, general animal behavior. I've always looked at animals going about their daily activities and kind of wondered what it would be like to be in their head and what they think about, how they go about surviving and doing the things they need to do. Also, since I was really little, I would be wandering around the backyard and find insects and look at them up close. These days I can't see anything this close, but I used to be able to do that. And I'd look at the amazing architectural design of insects' bodies and the coloration, and I was really curious about where that came from. So in all these, there was something interesting happening out in the natural world, and beyond just admiring it, I was interested in how would you do that? How could you make something like that? This was long before I was a computer, but my father was an avid model railroad builder, so the idea of scale models and little worlds, little constructed worlds, was something that I grew up with, and it melded very well when I started learning how to program. I'll also note that later in life, I got interested in the idea of the duality between graphics and vision, and being able to meld these two together. This was actually before the current explosion, the renaissance of computer vision work. It's a little hard to stay ahead of the research curve. So anyway, these are some of the places that I think these are all the places that I worked. One thing to take away from this is that I can't hold a job. I got a master's degree in '78, and then have worked at a selection of places. I guess longest tenancy was at Symbolics. I was there about 9 years, and Sony PlayStation R&D for 14 years. And some of the topics I've worked on in those many years. I started in school working on procedural animation. This was very early in the history of computer animation, and we were still trying to figure out how to do it, what the best techniques were. There was a lot of interest in what's known as keyframing, where you sort of an artistic technique where you sort of pose a character at one instant in time and another, and then use some sort of interpolation technique to get the in-betweening. This was sort of inspired by ideas from traditional animation. But there was also this notion that you might use a computer program, and so you, not merely to do interpolation, but to do the entire control problem. So a way to produce animation from the computer side, it was sort of a way of visualizing what programs are doing, or having animated visual output from programs. So these ideas seem as ordinary as dirt today, but they were kind of on the cutting edge back in those days. So I have worked on a couple of feature films and doing tools for that industry. I got interested in what's come to be known as behavioral animation, which is a sort of specialized form of procedural animation, where the objects are meant to be independent thinking, cognitively driven characters, autonomous characters. And that leads into having lots of those, and so being able to do collective behaviors of flux and school. Triangle mesh and point cloud algorithms, geometrical algorithms. I've worked some on game AI. Several of my projects have had some aspect of genetic algorithms in them, evolutionary optimizations. I did some work, I'll show a little, some of the experiments on stigmergy, collective construction or emergent teamwork. This is the sort of process that allows a colony of bees or of termites to build the structures that they live in that are necessary for their lifestyle. And kind of more recently, these last three are kind of in no particular order, but I mentioned the graphics vision duality, which led me to an interest in Camouflage, which is a natural system that has aspects of both, and procedural texture synthesis under evolutionary optimization, and vision. And I really have to pick up the pace here. So I'll start talking really fast. So yes, I did this thing called Boids, kind of a model of flocking based on individual agents. As an undergraduate, actually before I got to college, I was thinking about these ideas, but I wanted to know, how do birds flock? Would it be possible to build a simulation of that? And can the simulation be entirely at the level of an individual bird? You would assume that unless there's some unknown structure, force, communication going on, that somehow the individual animals in a flock of birds are behaving independently of the others just by perceiving their flock mates. So the question is, could you build that model in simulation to have a flock emerge from behaviors on the individual birds? Obviously, the answer to these questions was yes, or I wouldn't be here talking about it, but it was kind of an open question back then. I had we all have had these experiences that allow some thought experiments about what goes on when you're in the middle of a group of somethings, either a crowd of people or in traffic. So you can kind of think about what must go into that. But here was sort of the basic intuition. In a system like a bird flock here, look at an individual and imagine what it is perceiving in its world. In open space, the primary thing that they're looking at is the other birds. Of course, they have to worry about avoiding obstacles in the world and that sort of thing, going to and from, say, the nest in a place to find food or something. But we'll just talk about the simple case now. So bird perceives something about its environment and makes decisions about how to alter its path, to how to steer. And if you're able to do that, then you simply apply that to all the birds in parallel, or in simulation parallel, and you hope that it leads to a behavior like flocking. It would seem that a similar general principle would apply to something like a fish school, or to land animals running over terrain. So based just on thought experiments, it seemed like there were three basic components to the behavior of being an element of a flock. So these are illustrations of them. We're talking about the green fellow in the center there. The circle here indicates a neighborhood, although one of the interesting things, one of the slides I didn't make, was about how this notion of a neighborhood has changed over time. So I started with a spherical neighborhood, but there have been a lot of refinements, both in computer simulation, also in studies of real birds. There's this project called Star Flag, where they track thousands, tens of thousands of real starlings, and they've learned a lot from statistical analysis of those tracks. So in fact, the neighborhood is probably a fixed number of neighbors, not a distance. But anyway, come with me back to the days of the mid-'70s. So the idea was that there's a separation which could be thought of just as a sort of a repulsive field from your local neighbors. So we distinguish between the local neighbors and the ones that are too far away or too many intervening neighbors. So the red arrow here sort of indicates a desired behavioral force. There's cohesion, which keeps the group together. So separation keeps them spaced apart. Cohesion keeps the group as a whole together. And alignment keeps them going in basically the same direction. So cohesion, the idea was you find the local neighbors, you determine a centroid, and you have a behavioral urge to move towards that centroid. In alignment, you look at the headings or the velocity of your local neighbors, And so that's what this blue vector represents. And there's an error signal between the direction you're heading and the local average. And so you want to steer in a direction to zero out that error. Okay, so again, this was still at the thought experiment. There might have been some way of investigating this more formally, but you know, I'm a software geek, so there's only one way to be sure, and that was write code. This is actually a historical document. This is the original Lisp code that I wrote while at Symbolics. And to my great astonishment, it actually worked. This is an early motion test, so they're actually doing a slightly more complicated behavior. So there's the flocking, consisting of the three behaviors I was just talking about. They're also doing goal seeking and obstacle avoidance. So let's see. These are some very early motion tests. Ask you to forgive the prehistoric video quality. This was NTSC shot a long time ago and recompressed and transcoded, and you know, it's gone through quite a bit. So I didn't want to look at this whole thing, but here's just a group. They start in random positions. You see a little bit of flurry as they space themselves out the way they want to be, and then they're just flying along this road, or whatever that thing is. Whoops. Now what have I done? Okay. These darn computers. So this was sort of a zigzagging path. Here we see it view from inside the flock. This is around 1986, by the way, and these were captured. I believe this was just pointing a camera at the screen of my Lisp machine. Here's some obstacle avoidance against a plane. You saw stills of this simulation. So they're being drawn to a target up in this direction, and then there are cylindrical obstacles. You see that there's a lot of kind of confused flight as they approach the obstacles. So this is a very early attempt. And then this is a more refined version where they decide early on which side of the obstacle they want to head towards, and they aim towards the limb of the silhouette of the obstacle. All right. I think that's probably sufficient. And this work was done at Symbolics when it came out from being a midnight project. There was interest in pursuing it, so we built a system for doing 3D animation. And so there's this mysterious world out in the void, divided by a layer of ice. There's fish underneath and birds on the top, sets of planar obstacles on the bottom and cylindrical obstacles on the top. This is our hero Stanley, his love interest Stella. again, the fish and the birds mixed together. It's not physically accurate. All right. Well, my former coworkers deserve the credit. I need to move on here, so the credits are almost as long as the animation. So by 2006, this what had been 20 minutes of frame rendering was now a real-time activity. So this is a large Boids-like simulation running on a PlayStation 3. It's about 10,000 individuals. The update rate is 60 hertz, 60 frames a second. So it's a Boids model. There's other things going on. There's kind of a color imitation behavior happening. But anyway, progress. That was actually my programmer art, and this was the final version used in a demo for the launch of PlayStation 3 with fancy rendering and nice models, and working with a team of my coworkers to create this. Okay, so let me just speak briefly about this adaptive polyhedral resampling for vertex flow animation. So this was some work that I did around 91, still at Symbolics. The idea was to take something like a triangle mesh and be able to immerse it in a fluid flow and have the surfaces follow the flow by stretching or compressing as was necessary, remeshing, resampling the mesh. There's a little bit of revenge fantasy here. The paper was rejected by SIGGRAPH, and by now I think it's actually 3 SIGGRAPH papers have cited the unpublished paper, so yeah. This is kind of the idea. If you imagine taking a box and twisting the ends of it with insufficient mesh complexity, you get this kind of weird twisted thing, whereas you want to get kind of a screw shape like this. And the idea, and this will have kind of a deja vu of Boids. There are these simple local operations that happen on all the faces, edges in the mesh. And so, for example, when an edge gets too long, it's subdivided so the 2 adjacent triangles become 4. And when an edge is too low, too long and too short, determined by some parameters, then you just collapse it down to a point. This is a model that's growing in one place and contracting in another, and this is without the subdivision, and these are models showing different versions of the adaptive subdivision. This was used, pardon me, used to create little flow structures in an art film called Virtually Yours. So there's a video of this stuff, and for all of this, if there's any aspect of, I need to blast through, but if you're interested in more information on any of this, please feel free to contact me, just Google my name. This is a block that's been stretched out and folded over, maybe a little like taffy, and then stretched out again and folded over several times. Okay, so I mentioned stigmergy. This is the strategy by which lots of social insects can work together and have teamwork that emerges out of their individual actions and create large structures by working in parallel from local behaviors. So these are termite mounds. This is in Australia. They're often also common in Africa. But they're very large structures. The individual animals are, like a centimeter or 2 long, and they create these large structures, which seem a little lumpy and amorphous from the outside, but they actually have very elaborate internal structures, and they have something to do with regulating the temperature and humidity inside the nest, which is largely underground. The animals actually live mostly underground, but they have these big appliances like air conditioners that stick up above the ground. So this was an early simulation. The white cubes are meant to be little robots, and the colored cubes initially are spread over the world. So the robots go out and forage for blocks. In this case, this was sort of central place foraging. They were coming back to a certain location in the world at the global origin. They would originally just collect together the blocks, and then they would do this little behavior where they jumped up on that layer of, say, blue blocks, and would place another one on another layer, probably a little more clear in this one, and create these sort of organically shaped squat cones. I call them towers, but they're kind of bumps. This is a later model where the construction is, so it's not happening at a given location, but they pick up a block and they lay it down next to another block, and then they keep track of the largest pile they've seen during their lifetime, and they come back to it. So, for example, this tower being built here, and you see they've cleared a large, initially the world looks kind of like this with randomly scattered uniform density. And then they clear out those and start building their towers. These towers were built by guys who then wandered over and noticed that there was a bigger tower here, so they abandoned working on this. In fact, they eventually will disassemble these to add them to the greater glory of their favorite big tower. These are not simulations, they're just mock-ups of where I was going to go next with this. The idea of not just building a tower, but trying to build a somewhat more complicated structure of a wall. This shows a couple of little puck-shaped robots carrying one of these blocks. It's come upon the wall, and it's going to wall follow out to the end and look for a construction point. Here's, again, a couple agents carrying a block, and they're each recalling places where they recently placed blocks. These are potential construction zones, so they'll chat amongst themselves and decide where to go. All right. So the more recent work that I've done, and by recent I mean 2011, on the theme of closing the loop between graphics and vision, as I mentioned, I thought the evolution of camouflage was an ideal model system for this idea. It's sort of low-hanging fruit in the vision world. When I started planning this work around 2000 or 2005, computer vision was very much in its infancy, but it has had a spectacular bloom since then. So while this work might have been more significant to the history of vision, I think it's now kind of an also-ran. There are much more sophisticated things happening in computer vision these days. But the basic idea is to look at this coevolution of visual predators that identify prey by looking at the world and figuring out which parts of the world are actually food, versus the prey animals who would prefer not to be eaten, and the ones that are harder to see have more survival fitness, are more likely to reproduce because they're not being eaten. And the model used genetic programming as an evolutionary optimizer. There was a system for procedural texture synthesis. So if you're familiar with genetic programming, it's kind of a way of evolving programs. And in this case, I was evolving programs to do texture synthesis. Because I was ready to do the texture synthesis part before the vision part, I made this hybrid system as the first cut, and with a human observer in the loop playing the part of the visual predator. Okay, so here are some examples of camouflage evolved with the system. Each of these is a circle, a disk of synthetic texture, and then I've cropped a piece of the background environment. So this is some polished stone, this is lichen, these are some flowers from my backyard, this is my neighbor's hedge. There's lots of photographs out on the web, so I'm not sure quite, this is some kind of wire sculpture. This is tree bark, some lentils, and some beach pebbles. And in each case, there's one of the more effective, more interesting evolved textures is shown there in the center. So I said that this is a interactive hybrid system. So the human user is presented with a scene like this. There are 10 of the evolved prey overlaid on what's just a photograph of some natural texture. So this is polished serpentine stone. It happens to be the state mineral of California. It's also the stuff that's in the UN General Assembly chamber. You see this nice green wall behind the speaker. So you might be able to pick out 10 of them. This is towards the end of the simulation where they're starting to be fairly cryptic. Sometimes what you can see is the edge, and because you know they're a circle, so this is the idea of a search target. You sort of know what you're looking for, as a predator would. They kind of, so both the shape and the size would probably be known, and also you start to learn the particular camouflage patterns. So, but you can see if you can pick out all 10 of them there. Well, I'll present that challenge and then quickly change the slide. So, overall, this is kind of the notion that if you have a coevolutionary system, both sides are in an arms race to do better than the other one. If the prey are too conspicuous, they all get eaten. If the predators don't do a good enough job, or if the predators get fooled by the camouflage, then they starve. And so they, like the Red Queen, you have to run as fast as you possibly can to stay in one place. To simply survive, you need to continually improve your strategy. In the natural system, prey camouflage, I mean, I'm no biologist, but vastly oversimplifying, there is evolution acting on the morphological properties of the prey animal, affecting its overall shape and texture and color patterns. And in the predator, there's the visual system, the sort of the retinal processing, the image processing that goes on in the retina. There's the brain activity that helps understand those images. And of course, predators also have to have locomotion systems and weapon systems. And so the current version of the simulation is kind of like this with, as I mentioned, procedural texture synthesis being optimized by an evolutionary computation. And on this side, you have some poor schmuck clicking away. This kind of seems like an obvious thing to put on Mechanical Turk, although in these experiments, I actually was the schmuck. So just non-stop clicking for hours at a time. The way the experiment was, or the larger goal was for the predator side to be a computer vision system probably based on computational neural nets that would learn that the neural net would be training as the camouflage was evolving, and the hope was that both would then increase in quality over time. So I'll do a real quick National Geographic section here. So this is a little thing called a lanternfly. What I'd like to point out, so both the colors on its back are obviously a very good match for its forest canopy environment here. The bright greens like this moss, black like these shadows. There's a little bit of white here that corresponds to highlights off the damp, this is kind of a wet world. But particularly look at this edge here. There are these little features which sort of run perpendicular to the silhouette of the animal. And you'll even see places where it looks for all the world like a feature is just continuing across there. Oops. So this is referred to as disruptive camouflage, and it's particularly meant to interfere with the visual system's very low-level ability to find the silhouette of an object, to figure out, where's the foreground, where's the background, connecting together things into objects. So part of what camouflage does is defeat that. This is a camouflage doing this is a caterpillar doing a really good job of imitating the leaf that it's sitting on. This is a true bug on a piece of bark. This is a little fish on a sandy bottom, obviously very at home with its environment. This is an owl. It's actually two owls, so, but the mimicry of this bark pattern in the breast of the owl is pretty astounding. These are a couple of North American frogs. This one is from the northern area where you get a lot of, where you get cold winters and fall. We don't do fall in California, mostly evergreens out there. But for part of the year, things are kind of brown, whereas in the southern states, it's more humid and tropical, and everything's always green. So it's almost as though someone took this frog and dabbed a little green paint on it to retrofit it for this environment. This is a gecko. They hunt during the night, and during the day they just sort of glue themselves to a tree trunk and do a really good job of impersonating tree trunk. His head is down here. You can actually see his eyes. This is his tail. This is a leaf-tail gecko. They are amazingly cryptic. You can get right up to them and not notice them. And this is one of my favorite photos. So, how do you hide a 20-foot giraffe? You put him next to an acacia tree in the dappled shadow, and he blends right in. Okay. So blah, 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 there's stuff. A quick introduction to GP. This will be like the 10-second version. The idea is that you have expressions in a functional language. Here, they're just one-letter function names. So there's this one and this one. And so these represent two individuals in the population. And you want to cross them over to form some sort of combination of the two of them. You want to kind of blend them together in some sense. And what you do is random cut and paste, a really wacky notion, but you identify a sub-expression over here or a sub-tree of the parse tree is what's actually happening. And so you keep the red stuff here and the blue stuff here, and you drop the blue stuff in the middle of the red stuff, and you get a new expression that shares some functionality with the two parents. So that's literally all that happens to combine individuals. And in this case, the individuals represent a program that generates a texture. So you take two texture programs, you combine them like this to get a third texture program. And the population was divided up into sort of an island model. Green dots there indicating the individuals. I mentioned that there are cohorts of 10 at a time. We do cohort fitness, relative fitness of 10 individuals, so that's a subdivision of one of these demes. There's occasional migration between the demes, and the orange and green indicate the survivors from the previous generation, previous time step, and the new ones which have been recombined. And that process is shown like this. So the user is sitting at a screen and clicks on it and gets a display like this, which is a photographic background, in this case of some lichen. And as I mentioned before, there are 10 of these little circular prey. See when I have to start talking unbearably fast. So then the user picks the one that's most conspicuous. You know, what's the least well camouflaged one? So if you only had one chance to get a meal, that's the one you'd want to go for. So you click on it, it goes away, and then you repeat this process 5 times. One more. Okay, so of the 10 that were there, 5 have been eaten and taken out of the population. 5 remain, and then the 10 that are now gone are replaced using crossover, as I showed a moment ago. The typical run, there were between 1,000, 2,000 cohorts. At the lower bound, that's about 10,000 individual fitness tested. Something like 83 generations if you were doing a generational, but this is a steady state evolutionary computation. But yeah, the run comes down to about 5,000 clicks. So, you know, I would just sit there, I'd put some music on, and clickety, 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 click. Something like 3 hours of work for a run, not all in one sitting. I'm not crazy. So we saw some of these earlier. This is the Serpentine run. These are the Lantana flowers. Oh, and I should say that this is a time sequence. So this is early in the run, and this is late in the run. Sometimes they pass through, like this one or this one are really awfully good. This one's kind of nice. But, you know, so there's genetic drift, so they don't always, it's not a monotone increase in quality. Here's what a cohort looks like on the background. Again, so early ones just starting to, I left off some of the very early ones that are like, if you imagine purple stripes on a green background or something, it really wouldn't work in this. But as it starts to get closer to being effective on this background, here's 10 of them on the background. It's my long-suffering neighbor's hedge. So some of this stuff down here is looking very good. I was really amused to note this. You may be familiar that in graphic design, a really common trope is to do drop shadows, where you take the shape of an object and shift it over, and you have like a transparent gray thing. And anyway, it sort of invented the idea of drop shadows, which I thought was really cool. And then, so here again, 10 camouflaged prey on the background. Okay, and this is what it looks like when it doesn't work very well. This background, you can see the situation here. There's a mismatch between the size of the prey and the size of the features. This was an early run where I kind of learned that lesson. But all right. So in a couple of minutes, let me talk a little bit about research and industry. I'm happy with the fact that I've been able to do some research projects over the years, and that some of them have gotten traction, and things come from that, like, you know, people on the other side of the world say, come to our conference and give a keynote. And so that's kind of nice. But as a practical matter, I found it really hard to do what I'll call blue sky. I don't know if that's an Americanism, but research that's just, wow, that's an interesting problem. Let's let's try to simulate camouflage. And I'll point out that when I was working at Sony in the PlayStation R&D group, they didn't have a big need for simulating the evolution of camouflage. And so there's a tension between things that would make my boss happy and research projects that would make me happy. So tomorrow morning at this time, Stephen Wolfram's very smart guy, a very successful entrepreneur. He will probably have a different view of research and industry. And I guess if you're able to create a company and steer it in the direction that you want, then that's a good approach. But I just am not an entrepreneur. I don't have the skills or the temperament to do that. So I've always been, just a working stiff, a guy in a commercial operation. And like my current job, I am basically just a software engineer cranking away on some product. A couple of times, either explicitly or just because I tried to get away with it, I've done research, but when my job was officially research, it wasn't to do cool stuff, but it was, we've got this problem and we are thinking about that product, and can you come up with a way to do that? So it's very directed, it's very applied, and it's not what I think of as the most enjoyable, deeply satisfying kind of research. The stuff that I have done that I'm most proud of has always been off the books. When I was working on Boids, I was in charge of maintaining a system called S-Dynamics. It was sort of an animation scripting system. I was supposed to be fixing bugs and introducing new features. Instead I would sneak off, and I had an office in those days. I'd close the door and work away on Boids. The camouflage work was similar. I worked on that for about 6 months, literally at night and weekends, and time that I stole away from my family. Eventually, to his credit, my boss said, yeah, okay, you can work on that as part of your job. So I'm making these weird personal remarks because Oliver had suggested that this might be of interest to some of you early in your career. So I don't have any uplifting career advice to offer. So I worked on Boids at Symbolics and then eventually got laid off. Actually, they went out of business and I got laid off. And at Sony, they laid me off because they were having problems, and my boss had to get rid of so many % of his staff, and what's this person working on? Was this a critical project? What's this person working on? Critical is it? What's it? Oh, kind of camouflage and stigma. I don't know. So it's like having a target painted on your back. So when I was young, I remember this really corny public service advertising campaign, the tagline of which was, be cool, stay in school. So I'm at the risk of being as corny as that, I just want to encourage you all to think about not following the siren song of startups and the commercial world, but academia is a wonderful kind of cultural institution, and I would encourage you to consider staying there, and I would be there, but I made this bad mistake to leave after my master's, and once you're out, it's hard to come back. I keep coming up with plans to go back to school. So now I guess it becomes my bucket list. I'm kind of old. Some people, that world is exactly right. There's this guy, Teal, I can't remember his first name right now, but he actually gives scholarships. They're anti-scholarships. He selects people who are doing really interesting work and pays them money to drop out of school and go start a company. So I'm on the opposite side of that. I'd like to encourage you to if you're the type who loves pure research, I want to encourage you to consider an academic career, and is devote yourself to the quest for knowledge. I think that's a nice concept. So that kind of depressing view on industrial research aside, I just want to say thank you, and I appreciate your attention. So.